A modern construction site relies on digital blueprints translated into the physical world. The device bridging that gap is the total station. This instrument combines an electronic theodolite, which measures precise horizontal and vertical angles, with an electronic distance meter. Together, they calculate millimeter-level X, Y, and Z coordinates for any point in sight. But all that digital precision is completely worthless if the initial physical setup is flawed. The machine doesn't know where it is until you tell it. To establish that position in the field, we need a few key pieces of gear: a sturdy tripod, a leveling base called a tribrac, a prism pole, and 2 established control points on the site. Nailing this initial calibration dictates whether your project is built exactly to spec, or if you'll spend weeks tearing out and redoing concrete due to a fraction of an inch error. Step 1 is positioning the tripod. Extend the legs to about chest height so you can work comfortably, and stake them firmly into the ground directly over your first control point, what we call the occupied point. Next, thread the tribrac onto the tripod head and place the total station into it. Tighten the central bolt underneath to lock the instrument onto this stable platform. To ensure we are exactly over our occupied point, we use a built-in tool called a plummet. On modern instruments, this fires a laser straight down from the vertical axis. If that red laser dot is missing the mark, slightly loosen the tripod's center bolt and slide the entire base across the flat head of the tripod until the laser hits the exact center of your control nail. Then lock it back down. Getting the physical center close right now means you won't have to push the fine leveling screws to their mechanical limits in the next step. Power on the total station and navigate to the digital level screen. This displays a sensitive electronic bubble, showing real-time tilt data across 2 perpendicular axes. This field manual excerpt outlines the strict leveling procedure. Rotate 2 of the foot screws simultaneously and in opposite directions to move the bubble along a single axis until it is centered. Then use the 3rd foot screw all by itself to dial in the remaining perpendicular axes. Keep adjusting until the digital target is locked in the center. Here is where many operators make a mistake. The very act of turning those leveling screws actually shifts the instrument slightly off the ground mark. You have to check your laser plummet again. If the laser wandered off the nail, you enter the centering loop. Loosen the base, gently slide the instrument back to the exact center, tighten it, and then re-level the foot screws. You repeat this loop until both the level bubble and the laser plummet are perfectly aligned at the exact same time. Accepting anything less here bakes a permanent, systematic error into every single measurement you're about to take. With the instrument physically planted, grab your data collector. Create a new job file and define your project's coordinate system, which organizes space into northing, easting, and elevation. Next, tell the software exactly where the instrument is standing by inputting the known coordinates for your occupied point. Then pull a tape measure from the ground nail straight up to the trunnion axis mark on the side of the total station. Enter this value as the instrument height so the software can accurately calculate true ground elevations. The instrument now knows where it is, but it doesn't know which way it is pointing. To orient it, we perform a backsight by targeting a second known control point. Have a crew member place a prism pole on that second point. Aim your crosshairs directly at the center of the prism, then enter the backsight point's coordinates and the height of the prism pole into the data collector. Once you lock that in, the instrument is officially oriented. Every degree of rotation the machine makes now perfectly aligns with a fixed, real-world grid. You are finally ready to map the site. Direct the rodman to carry the prism pole to a physical feature you want to record, like a building corner or a topographic break line. Sight the prism through the telescope, type in a descriptive feature code, like BLDG for building, and hit the measure button. These geometric diagrams illustrate the math happening inside. The microprocessor takes the slope distance measured by the laser, combines it with the precise vertical angle, and instantly calculates the exact horizontal position and elevation of your target. That measurement is saved as a precise XYZ coordinate, a permanent digital record of the physical world. Open up the point list on your data collector, and you will see the results of that work, a neat column of northing, easting, and elevation data, all organized by your feature codes. A complete topographic survey is just a matter of repeating this sequence, moving the rodman from point to point until all the necessary site features are recorded. Back in the office, you export this field data via USB or a cloud server directly into software like AutoCAD Civil 3D, where those points are used to draft final plans. Because you took the time to meticulously level, center, and orient the total station, you now have an exact, reliable digital twin of the job site, giving you total control over how the rest of the project gets built.